All right, so in today's buffer lab, you are going to create a buffer of sodium acetate and acetic acid, and you are going to determine the buffer capacity of two different buffers. We're going to first create buffer A, which is going to consist of 0.1 molar acetic acid and a calculated amount of the salt sodium acetate. And then we are going to test buffer B, which is 1 molar acetic acid with calculated amount of sodium acetate as well. All right, so now we're going to prepare buffer A. And buffer A is using the 0.1 molar acetic acid solution. So first, I'm going to take our measured mass of the sodium acetate, which is the conjugate base. So I've got my solid in the volumetric flask, and I'm going to slowly pour the acetic acid in. All right, so now on to buffer B. All right, so that's our buffer B. Okay, so we're ready to start our first trial. I've got 10 milliliters of buffer A, and I added 30 milliliters of water. And we discussed last time how the pH probe needs to be submerged, so the 10 milliliters of the buffer wouldn't be enough volume to do that, so that's why the water is necessary. I've got a stir bar. I've got sodium hydroxide as the titrant in the burettes, so that's ready to go. And I've got the LabQuest set up, and we're going to be recording the volume increments so that we can plot a pH curve. So here we go. Oh, actually, let's keep the first point. And this is with 0 milliliters added. Okay. The goal is to find out what the capacity of the buffer is. And by capacity, it means how much neutralization can take place, how much titrant it can withstand before the pH changes by 2 units. All right, so we've gone about 1 pH unit above where we started. This buffer A has a lower number of moles in it, so I'm taking my time because each drop is going to be more influential. And so now we're starting to see huge jumps. And we'll wait for the pH to kind of settle itself. The closer we are to the equivalence point, the more each drop makes a difference. And the farther out we are from the equivalence point, the less it matters. Okay, so after trial 1, in analyzing our graph, we need to figure out 2 things. We need to figure out the volume needed to change the pH by 2 units. So if we look at where we started, our pH started at 4.9 when we started recording. So the closest we get to that would be a pH of 6.9. And so that would be somewhere in between this stretch. So we go from a pH of 6.6 to 9.6. So we're gonna go with the volume at 6.6 because that is the closest point that we have. And the recorded volume was 1.74 milliliters. So that would be our recorded volume needed to change the pH by 2 units. The second thing we need to find is the equivalence point, the volume for the equivalence point. So to do that, we would go to a table and we would create a new calculated column, and we would call it first derivative, or just to be lazy, I'm just going to say D1, because we could also do a second derivative if we want to, but I don't think it's going to be necessary here. D1 for first derivative. And the equation we choose would be the first derivative. And what we do is we look for the inflection point, right? Because the inflection point, that is the point in which the rate of change changes from being positive to negative. So our volume at the inflection point is the midpoint of the vertical leap, and that's at 1.87 milliliters. So that is the volume for the equivalence point. All right. Okay, so this is the second trial. This is buffer A, but this time we are going to be titrating with 0.5 molar HCl. And so our methodology is going to be the same. All right, so that's well past 2 pH units. We'll stop that run. Okay, so we just finished trial 2, which was buffer A with 0.5 molar HCl. And if we look at our data table, this was run 2. Our starting pH was 5.03, so we want to find when our pH got to about 5.03, or 3.03, sorry, which was 2.44 milliliters. So that's what we're going to record as the volume needed to change the pH, to lower the pH by 2 units, 2.44 milliliters. Okay, so now we are moving on to buffer B, and we are set up with 10 milliliters of the buffer, 30 milliliters of water, and we are now titrating with 0.5 molar sodium hydroxide as the standard. So given that the concentration is much, much higher, I'm going to use larger initial amounts. So okay, so we finished our titration of buffer B with the sodium hydroxide. And so what we need to find is the volume at which the pH changed by 2 units. So the easiest way to find that would probably be to look at the data table. So this was run 3, and our starting pH was 5.1, so we're looking for 7.1. So our pH we have 7.02 and 7.23, which we're looking for the pH that's exactly right in between these two. So 7.8, 18.0, I would say that we could split the difference between these two and call the volume 17.9. 17.90 would give us a pH of 7.1 approximately. So we're gonna go with that. Additionally, we want to find the volume at the equivalence point. So we can take the derivative. Actually, let's connect the points. That might make it easier to see. So we go to the menu. Oh, actually, I think it might still be there. Yep, D1. So the derivative for run 3 occurred at a volume of 19 milliliters. Okay, so this is our last trial. This is our buffer B with 0.5 molar HCl. And as before, the concentration is much greater, so I'm going to start with larger increments of HCl. We're going to do approximately 1 milliliter at a time. Note the initial pH, 5.09. Okay, so now let's check the table and see how much it took to lower the pH by 2 units. So this is round 4. We started with a pH of 5.1. And we're looking for 3.1. And we do not have exactly 3.1 yet again. But we have 3.24 and 2.99. So if we bisect the difference here, 3.1 would occur approximately halfway through here. So halfway through 0.4 and 0.9, let's see, this is 0.5, so that would be 21.65 approximately. So we can use 21.65 as our volume to lower the pH by 2 units.